the title is basically going to be probabilistic graphical model for statistical inference. I'm actually going to be guided by this outline where I'm going to talk about the essence of modeling. I'm going to make a distinction between machine learning and data science. I'm also going to differentiate between explanatory power and the predictive power. Then from there, basically going to justify the essence of probabilistic graphical model. Then I'm also going to talk about the graphical model in overview. Then from there, I'm going to move to applications where I'm going to touch weather forecasting, uh, you know, stock returns, and so on like that. Then I'm also going to showcase my recent research. Then I'll finally make conclusion. Okay, the essence of modeling. I'm going to say we find ourselves in a world uh, where things are changing. There's a lot of variations in this world. And because of that, I'm actually going to say we live in a stochastic environment. We live in a probability space. And you know what? How do we take decision in this environment, decision that we do not want to regret? Okay, then it means we basically need knowledge. And you know what? It is the information that we translate into knowledge. Okay, now where do I get information from? And that is the reason why we need to collect data. And when data are said are collected, we don't have access to the information immediately. And of course, something needs to be done, to extract the information that we need from data. Okay, like I said, it is information that will translate into knowledge that will enable us to understand either our political environment or medical environment or psychological environment or whatever environment. Okay. Now, the next thing I want to talk about now is, machine learning, data science, variant of statistics. I'm basically going to call machine learning data science variant of statistics because they also use the principle of statistics. I'm basically going to say with the evolution of Facebook, uh, you know, a lot of data set have been kind of generated every minute, every second, every day. And in fact, I can authoritatively say that more than 90% of the data set in the world today were actually created within the last 5 years. And what actually happened is that statistical models struggle with, big data and statisticians did not adequately respond to advancement in technology, and the machine learning expert actually took advantage of that. Well, let me tell you this: whether we're talking about machine learning or we're talking about statistics, they all learn from data, or only that the way they learn from data, they learn from data in different ways. The statistician we specify a model, okay, but the machine learning experts will use algorithm to learn the model from data. Okay, and of course, the two of them have a way they validate, what the resulting model. Okay, I want to talk about explanatory power and predictive power. Actually, it was argued in 1948 by Empire and Oppenheim on their paper called the Studies in the Logic of Explanation, where they argue that the explanatory power it should be equated to predictive power. But it was until 1959 when Emma and Resha noted, in their paper called on the epistemology of inexact sciences, they actually observe that as uncertainty associated with explanatory is actually different from the one associated with predictive with prediction. And of course, I just want to say this: there's a difference between the two, in the sense that a model could have a predictive power, but may not have an explanatory power. And I can actually say here authoritatively that science, statistical model has more of explanatory power compared to the machine learning algorithm, and why the machine learning algorithm has more predictive power than statistical model. Okay, we shouldn't mix model explanation to model predictability. Okay, in 2000, and in fact, in 2001, Simon, in his paper called Science Seek Parsimony, not simplicity, searching for pattern phenomena, Simon actually noted, he likened the relationship or the distinction between the explanatory power and the predictive power to the difference between basic science and applied sciences. In basic sciences, we try to understand and describe the world, but why in applied science, we use the law connecting variables to basically make an inference. Okay, so to buttress my point on the distinction between the explanatory power and the predictive power, of course, Bremen in 2001, in his paper on statistical modeling the two cultures, he noted that statisticians ignore algorithmic modeling. Okay, I'm basically going to say this. The algorithmic modeling is not interpretable, but what, the facts remain that they have a high predictive power compared to data modeling used by statisticians that have more explanatory power. Okay, so, and what I just think we can do is, what is going to make a whole lot of sense, and what we actually be scientifically useful is how can we actually translate an explanatory power, okay, into predictive power. I think that is what I think we should be doing at this point in time. And of course, the one of the machine learning technique that I'm actually going to be spending more time on today, that I call the probabilistic graphical model, is actually a way to attain what I call interpretable machine learning. Okay, so why probabilistic graphical model? I'm going to say this, generally we got two ways of learning from data. Okay, the number one conventional way of learning from data is actually to find a function, okay, a function that map directly input value to its class value. Examples of such function could be linear regression, decision tree, or random forest, and so on like that. And another way of learning from data is basically to find a probability distribution over random variables. And of course, the distribution can then be used to, we can query the distribution, to answer a question about a new data point. But you know what? Using probability distribution, okay, to model random variables has led to gain efficiency. But the issue with that is it could lead to it's computationally intensive in the sense that when the numbers of the probability joint distribution is actually exponential to the numbers of states or cardinality in the feature. I'm talking about high dimensional data set. We basically using that conventional approach, we basically going to have a lot of parameters to be estimated in the sample space, in the parameter space, and at times that could be difficult to undertake. And we needed to have a technique that can compactly, capture, that in a way that we're going to have a drastic reduction in the parameters that will be estimated. Okay, and that is what we call the probabilistic graphical model. Okay, the probabilistic graphical model, we capture conditional independence relationship, between interactive random variables. And of course, it does that, by actually use a combination of multivariate probability distribution using graph. Okay, so why do we need a PGM? So in the machine learning world, so like I said, it actually provide the structure where we can actually leverage, the independent property to represent the high dimensional data in a more compact way. So it's actually a powerful tool that we can use to draw inference on some, when you have unobserved variable giving the evidence unobserved. Or, for example, I want to figure out how in image processing, maybe I actually, travel to my grandparent place and I saw an old picture. The old picture, of course, is going to be noisy, right? And I actually want to figure out what is the probability of the original image given the noisy image. That is what I mean. Okay, so types of graphical